In our previous example, we used multidimensional Newton's method, but in many instances, it's actually not possible or not very efficient to find a closed formula for the Jacobian matrix, which is what we actually need to use Newton's method. So in these particular cases, what we can turn to instead is finite difference approximations. So we can actually estimate each of the entries in the Jacobian matrix, and the resulting method is called approximate Newton's method. So here's the idea. Let's suppose that the Jacobian entries have indices I and j, and what this means is that we're talking about partials in the following form. So that's going to be dfi by dxj. I'm using x for every single dependent variable here. So essentially what we want to do is we want to estimate these partial derivatives using a finite difference approximation. So that would be something like this. We define dfi by dxj as some delta j times fi. So we want to actually have a delta multiplier to the function. So essentially, and I should be doing an approximate sign here. Essentially what we're saying is we'll do a finite difference. So we'll say that this is fi at point xj plus h minus f at xj. There we go. And this is all going to be divided by h, where h is obviously some small number. Okay, so let's do the example that we had in the previous session, the example with the two functions, one of them being an ellipsis. Let's do it once again. So just to remind you what we had. So f1 of x and y was defined as y minus 0.2 times e to the 0.2x plus e to the minus 0.2x, like so, and that was equal to 0. And then the other function f2 of x and y was defined as x squared plus 4y squared minus 16 also equal to 0. So once again, we're looking for the intersection point, and we have some starting coordinates. So just like last time, the starting guess is that x of 0 is equal to 3 and y of 0 is equal to 0.5. Okay, so armed with this and the knowledge of finite differences, we can actually try and get our deltas. So delta, first of all, we're going to have delta 1, so 1 f1, that's going to be the following. And once again, we're going to have a fairly long fraction, so I'm going to draw a very big line here. Okay, so that's going to be fi at xj plus h minus f at xj, all divided by h. So that if we plug in f1, first of all, that's going to be something like the following. So it would be minus 0.2 times e to the 0.2. And here we have x plus h plus e to the minus 0.2 x plus h. So all of this plus 0.2 times the original f at xj, so that would be e to the 0.2x plus e to the minus 0.2x. And all of this is divided by h. So we can collect the terms a little bit. We can take out the 0.2, so that's going to be 0.2, and I'm going to draw another line just as big almost. So that's going to be 0.2 multiplied by e to the 0.2x plus e to the minus 0.2x minus e to the 0.2 x plus h minus e to the minus 0.2 x plus h, all divided by h. So we got an expression for delta 1 f1. Now we want an expression for all the other parts, because remember the Jacobian has 4 terms. So this was df1 to dx, and this was df1 again to dy, and this was df2, same here. So we need 4 terms, but we only got 1 of them. So let's do the other ones. So the other ones are going to be a bit easier. So delta to f1 is quite simply y plus h minus y divided by h, so that's equal to 1. Now, why is it this particular amount? Let's take a look at what's actually happening. So for the second delta, we're actually using the index 2 here. So the index 2 here is essentially the index of x2 in our notation, but because we have a function of x and y, essentially what happens, these x and y, they map onto x1 and x2. So essentially all that's happening when we talk about x2 is we're getting the y value. So that's why we get y plus h minus y divided by the h, and that's equal to 1. And the other values are equally easy. So delta 1 f2 is equal to x plus h squared minus x squared divided by h. And then delta 2 f2 is equal to 4 times y plus h squared. I should probably move this out the way because it's kind of overlapping what we're doing here. I'll do it a little bit lower. So that's 4 times y plus h squared minus 4y squared, all divided by h. So now we have all the 4 delta times f products. And now we can actually express the determinant. So we can calculate delta f, the actual equivalent of the Jacobian. So this is the determinant of the following. So that would be delta 1 f1, delta 2 f1, delta 1 f2, and delta 2 f2. And this is where we plug in everything that we've written so far. So that's going to be a rather large thing, and I don't really want to sort of copy over this particular bit, so I'll just call it sigma for lack of a better word, and I'll copy the other ones though. So we'll have sigma, here we'll have a 1, here we'll have x plus h squared minus x squared divided by h, and here we'll have 4x plus, that's y, 4y plus h squared minus 4y squared, all divided by h. So we need to calculate the determinant of that, and that's going to take quite a bit of time. I'm not going to show the workings here because sigma is really large. Let's just assume that we'll keep the function somewhere. Actually, why not? Let's write it out. So it's going to be 0.8 multiplied by e to the 0.2x plus e to the minus 0.2x minus e to the 0.2x plus h minus e to the minus 0.2x plus h. So that's this part, and then all of this gets multiplied by the following. So we have y plus h squared minus y squared. So this is divided by, I better do a nice line if I'm going to draw this. This is all divided by h squared, and subtract from that x plus h squared minus x squared divided by h. So this is essentially the determinant. So it's this sigma thing times this bit, minus this part multiplied by 1. So here it is. Okay, so now that we have an expression for the overall delta here, what we can do is we can choose some tolerance, we can choose some h value that we're happy with and use that as a kind of finite difference. So for example, we can say, let's have h being equal to 10 to the minus 6. So now, armed with this value, what we can do is we can calculate delta x and delta y, and that's what we need for the actual iterations. So first of all, we'll calculate delta x, and delta x is essentially the idea of taking the values, the delta values, and plugging them in. So this would be essentially defined as the following. Once again, a very big fraction coming up. So that would be minus f1 at x0, y0 multiplied, and remember we had the partial derivatives here at a particular point. Well, not anymore. This time we replace it completely, and we replace it by the product of the delta, in this case delta 2, and the function f2 at y0. Plus, and we'll have the function f2 at x0, y0 times delta to f1 at y0, all divided by delta f at x0, y0. So after we substitute the values, we end up with 0.9838. And then the same goes for the delta y. So delta y in this case, and we had the formula before, once again, big line here, that's essentially minus f2 at x0, y0 times delta 1 f1 x0 plus f1 x0 y0 times delta 1 f2 at x0, all divided by delta f x0 y0, and that's equal to roughly 0.0243. So we now have the values of delta x and delta y, and afterwards we just repeat the process as we did before. So essentially we say that we have a new estimate for x1, a new estimate for x, which is x1, which is x0 plus delta x, and we calculated delta x up above. So that's essentially, remember x0 was 3, so the x1 is 3.9838. And similarly for y1, that's y0 plus delta y, and that's equal to this value plus 1/2, so that's 0.05243. Actually, I put an extra 0 in here. Let's have it like this, 0.5243. And then, of course, what you do is if you want refinements of x1 and x1 and y1, then you plug in the values once again. You go through the entire process and you keep iterating until you get until the change becomes sufficiently small that you are happy with the result. Alright, so here we go again with calculations in MATLAB, and this time you're not going to find any differentiation in here, because essentially, apart from defining the functions themselves, as we did previously, all we're defining is we're defining the initial guesses for the x and the y. We're defining some sort of error tolerance that we're happy with at some point at which we're going to stop, and then we perform a certain number of iterations. Now the h value is defined as 10 to the minus 6, and we're prepared to iterate 5 times in order to find the new values. So here are the finite difference calculations for d1, f1, d2, f2, and so on, and then we plug those to calculate the actual determinant. So this is the Jacobian from the finite differences. Then we calculate delta x and delta y. We calculate the new guesses for x and y, and then we look at how much they've changed, and if the change is less than what we wanted, which in this case is 0.01, then we stop. So as I run this, you'll see that in just 3 iterations, we managed to satisfy the error requirement, and we also got our actual results.